In this video, I'm going to talk about bigO. bigO time is the metric we use to describe the efficiencies of algorithms. It is used to describe the execution time required or the space used by an algorithm. bigO notation indicates the upper bound. So if we write O of f of n with large value of n, runtime is not more than f of n times a constant. First, let's talk about time complexity. Time complexity describes the execution time by an algorithm. The most common complexity include O of n squared. O of n squared increase very fast as n increases. And this is also called quadratic time complexity. The second is O of n, also called linear time complexity. The runtime increases linearly as n increases. O of log of n is better. And the best here is the constant time O of 1. We also have others such as O of n times log of n and O of 2 to the n. Now let's look at some examples. Given a function, namely linear, with an array integers, we have a loop and we loop through the array and print the elements in the array. As the size of the input is n, so there are n iterations. And the time complexity is O of n. Now we talked about space complexity. Space complexity describes the space used by an algorithm. Let's look at this example. We have a function, namely factorial, that is used to compute the factorial of n. If n is equal to 1, then return 1. Otherwise, we would have to do something. We return n times the factorial of n minus 1. So we call the function, inside the function, we call to the function itself and give it the parameter n minus 1. And this is recursively computes the factorial of n. Let's take an example. If we compute the factorial of 4, so we give 4 to the function. Looking at the call stack, we call factorial of 4. In the function, it then called to factorial of 3. And then in factorial, again, it calls to itself and give it 2. So it calls to factorial of 2 and then factorial of 1. So this actually takes actual memory. The space complexity here is O of n, and n is the size of the input. Let's look at another example. In this example, we have a function, namely pair sum mean. We initialize a variable sum with 0 and then loop for all the values from 0 to n minus 1. In each iteration, we call to another function, namely pair sum. Pair sum returns the sum of 2 consecutive elements. The return value is then added to sum. And this is iteratively called. So here we take O of n calls to pair sum, but only O of 1 space was used at the calls don't exist simultaneously on the call stack. How do we analyze time and space complexity if there are multiple paths, loops, etc. in the algorithm? So let's look at this example. We have a function. The function is named linear with the parameter integers. And we have 2 loops. Are we going to write the time complexity O of 2n? So the first principle is to drop the constant. So if you have 2n or something times n, you drop that constant. And so the time complexity is O of n, and that's it. The second principle is to drop the non-dominant terms. In this function, namely quadratic, we have a loop, and next we have 2 nested loops. So are we going to write the complexity O of n squared plus n? Actually, because n is a non-dominant term, so we drop it. And the time complexity is finally O of n squared. If you have multiple parts in your algorithm, you may add and also multiply. Looking at the example, if you have two loops separately, then you add n together. So it's going to be 2n. And if you have two loops nested, then you multiply together. So you have O of n squared. Actually here, O of n squared. So finally you write O of n squared plus 2n. And applying the second principle, you drop the second term, and finally you have O of n squared. There are also other runtimes. Let's look at this example. We have a function f of n. If n is less than or equal to 1, then return 1. Otherwise, return f of f with the parameter n minus 1 twice. And return the sum of them. So looking at the tree, this is level 0, and the next is level 1, the next is level 2, etc. At level 0, we have one node, or we can say 2 to the 0 node. At level 1, this level, we have 2 nodes, or 2 to the 1 node. At level 2, we have 4 nodes. Four can be written as 2 squared. We repeat this again and again until we have all ones. So looking at the sum of 2 to the 0 plus sum of 2 to the 1 plus sum of 2 squared, etc. up to 2 to the n would give 2 to the n plus 1 minus 1. We dropped the constant, and finally we have O of 2 to the n as the time complexity. And it is actually O of the number of branches to the power of the depth. Another runtime is O of log n. Let's take an example, which is a binary search. Given an array, or in Python, it is a list. And given the key, which is the key that we are searching for in the array. So binary search works like this. From the low value and the high value, we compute the mid value. The mid value here is 50. We compare the key and the mid value. If the key is less than the mid value, then we take the first part. And if it is greater than the mid value, then we take the second part. Key is 11. So key actually is less than the mid value, which is 50. So we take the first part. And this is the first part. Here it is. And we repeat again recursively with the low and the high values. We compute the mid value and compare the key with the mid value. The key is 11 and it is greater than 7, which is the mid value. So we take the second part, which is here, and recursively repeat this again. The low value is here and the high value is there. We get the mid value. And the mid value here is exactly the key which is searched for. And the algorithm finishes. So if the size of the array, let's say n, is equal to 8, then in the second step, we have half of it left. So n is 4, and then n is 2, and then n is 1. If we reverse this, looking at the reverse order 1, 2, 4, and 8, 1 is actually 2, 0. 2 we can write 2, 1. 4 we can write as 2 squared, and 8 we write as 2 cubed, and etc. The power is actually the number of steps of the dividing steps and also the time complexity. If we call it k, then we can pull out k, and k is log of n, taking the log of both sides of the equation, you get k. So k is log of n, and that is the time complexity.